Open your earthquake app this week, and the map looks almost impossible to ignore Colombia, Indonesia, Japan, Spain, and the United States all lighting up within days of one another. Some of these earthquakes were destructive. Others were moderate, deep, or relatively local. But when the alerts arrive one after another, it is natural to ask whether the planet is entering a new phase. The short answer is more complicated and less apocalyptic than the headlines suggest. To understand what is happening, we need to separate coincidence, plate tectonics, aftershock sequences, depth, and genuine regional hazard. On August 10, a magnitude 7.4 earthquake struck western Colombia near San Jose del Palmar in Choque. USGS placed the hypocenter at roughly 110 kilometers depth. The earthquake was powerful enough to be felt across a broad part of the country, and the human consequences became severe. By August 20, reports described more than 300 deaths and widespread housing damage. This was not simply another dot on a global map. For Colombia, it was a major disaster, and its location beneath the western Andes placed it inside one of the most complicated tectonic regions on Earth. A depth near 110 kilometers means the rupture occurred well below the shallow crust. Deep earthquakes often spread, shaking over a wider region because seismic waves can travel efficiently through dense rock. But depth does not make a large earthquake harmless. Magnitude, distance, local geology, building vulnerability, and the way seismic energy reaches the surface all shape the final damage pattern. Colombia sits where the Nazca Plate converges with South America, while other blocks and faults complicate the picture. That geometry produces both shallow crustal earthquakes and deeper events inside the descending slab. 4 days later, another major event struck Indonesia. A magnitude 7.7 earthquake ruptured near floors in East Nusa Tenggara, with a shallow source close to 10 kilometers deep, according to USGS. A tsunami warning was issued and later lifted after relatively small waves were observed. Landslides, damaged buildings, blocked roads, and repeated aftershocks turned the first shock into a prolonged emergency. By the following days, at least 53 deaths had been reported. The contrast with Colombia is important. Similar large magnitudes, but very different depths, fault environments, and local consequences. After the floor's main shock, hundreds of aftershocks followed. That is expected after a major rupture, because the surrounding crust must adjust to a new distribution of stress. BMKG then recorded repeated felt earthquakes around Rutan and Manggarai on August 19 and 20, including events in the magnitude 5 range and numerous smaller shocks clustered in the same broader region. To someone watching a global feed, that can look like the entire country is suddenly breaking apart. To seismologists, much of it is the recognizable behavior of an active earthquake sequence. Indonesia lies across an extraordinary collision zone where several major plates and smaller tectonic blocks interact. Subduction, strike-slip faults, volcanic arcs, and back-arc structures overlap across the archipelago. That is why earthquake and tsunami hazards are not anomalies there. They are expressions of the same plate motions that built the islands, volcanoes, mountain ranges, and deep ocean trenches. The key point is that Indonesia's activity does not need a mysterious global trigger. Its local tectonic system already stores enormous strain and releases that strain through earthquakes on many different faults. Japan also appeared repeatedly on earthquake lists. JMA's August catalog includes magnitude 5 class events off Omori, Hyuga, Nada, Kumamoto, Sanriku, and Awat, among many smaller earthquakes. And just before August, on July 28, the Kumamoto region experienced a damaging magnitude 6.8 earthquake. That recent memory makes every new alert feel more ominous than it might in isolation. But Japan is one of the most instrumented seismic regions on Earth, so even moderate events are detected, located, and reported rapidly. High visibility can amplify the impression of constant escalation. Japan is positioned near the meeting zone of major oceanic and continental plates. Offshore subduction creates the possibility of powerful megathrust earthquakes, while inland faults generate damaging crustal events. This means two Japanese earthquakes, separated by hundreds of kilometers, may belong to completely different fault systems. A national map can make them look connected even when their physical causes are local. What scientists watch for is not simply the number of dots. They examine location, depth, fault mechanism, migration, aftershock patterns, deformation, and whether activity departs from the long-term background. Then Spain entered the headlines. On August 14, a magnitude 5.2 earthquake struck near Utrera in Granada at about 10 kilometers depth, producing very strong local shaking in the USGS intensity estimate. Damage was reported to building facades, and the earthquake was felt across parts of Andalusia. For residents, a magnitude 5 event directly beneath a populated area can be much more alarming than its number suggests. Spain is not on the Pacific Ring of Fire, but it is not tectonically quiet. Southern Spain sits near the broad zone where Africa and Eurasia converge across the western Mediterranean. The Mediterranean belongs to the wider Alpide earthquake belt, which stretches from Southeast Asia through the Himalayas and into the Mediterranean. USGS estimates this belt contains about 17% of the world's largest earthquakes. The faults here are complex because plate convergence is distributed across many smaller structures rather than one simple boundary. That produces earthquakes from Turkey and Greece to Italy, North Africa, and Iberia. So Spain's earthquake belongs to a known tectonic setting. Its timing near events in Indonesia or Colombia is dramatic on a calendar, but the underlying fault systems are thousands of kilometers apart. The United States was on the same alert maps. On August 13, a magnitude 3.8 earthquake occurred near San Leandro in California, while Alaska had a magnitude 5.6 event northwest of Squinta on August 8. These are very different earthquakes. California's event was small but close to a dense population. Alaska's was larger, yet location and population exposure strongly influence how an earthquake is experienced and reported. A single country can contain transform faults, subduction zones, volcanic regions, and intraplate seismicity. Putting every American earthquake into one category hides the geology that actually matters. Now step back from individual countries. About 81% of the world's largest earthquakes occur around the Pacific seismic belt, better known as the Ring of Fire. Another major concentration follows the Alpide belt from Indonesia toward the Mediterranean. When several active segments rupture within a short period, headlines can jump from one continent to another without requiring one event to cause the next. The geography is connected by plate tectonics in the broadest sense. But connected geography is not the same as a synchronized global earthquake mechanism operating on a weekly schedule. This is the central question: are earthquakes actually becoming more frequent? USGS says temporary increases and decreases are normal fluctuations and are not evidence that a larger global earthquake is about to happen. The National Earthquake Information Center now locates about 20,000 earthquakes around the world each year, roughly 55 per day. Most are too small or too remote to make international news. Modern networks also detect more small earthquakes than older networks could. Better instruments, faster communications, smartphones, and social media mean we now see seismic activity almost in real time. Long-term records provide a useful baseline. USGS expects roughly 16 major earthquakes worldwide in an average year, about 15 in the magnitude 7 range and roughly 1 magnitude 8 or greater. Some years exceed that average and some fall well below it. Random variation is expected in any process where rare events occur across many independent fault systems. That means a dramatic 2-week cluster should be compared with decades of data, not just with the previous quiet week. Human memory is short, tectonic statistics need a much longer window. Scientists have tested whether apparent global clusters of large earthquakes require a special worldwide cause. A USGS published statistical study found that random variability plus localized aftershock sequences can explain the observed timing remarkably well. Think of it like storms in different oceans. Several can exist at once because the planet contains many active systems. Their overlap in time does not automatically mean they share one trigger. The same principle applies to earthquakes. The world has thousands of active faults. Occasionally, several significant ones rupture close together in time, creating a powerful psychological sense of pattern. There is one important nuance. Large earthquakes can sometimes trigger seismic activity at distant locations through dynamic stress carried by passing seismic waves. But USGS notes that these remotely triggered events usually occur in places already close to failure, and the triggered earthquakes are commonly small and short-lived. This is not evidence of a planet-wide domino chain. So scientists do not assume that Colombia caused Indonesia, or that Indonesia caused Spain simply because the dates are close. Demonstrating a physical trigger requires specific timing and seismic evidence. Another reason headlines can mislead is that magnitude is only one property of an earthquake. It measures the size of the source, not the amount of shaking every person experiences. A shallow magnitude 5.2 beneath a city can produce intense local shaking. A much deeper magnitude 7 earthquake may be felt across a huge area, but distribute its energy differently at the surface. Distance from the fault, soil conditions, basin amplification, building design, landslides, and population density can turn similar magnitudes into completely different disasters. Large earthquakes rarely occur alone. They are followed by aftershocks as the crust adjusts to the changed stress field around the rupture. A major main shock can generate hundreds or thousands of smaller earthquakes. Those events can dominate regional earthquake feeds for days, weeks, months, or longer, depending on the size of the rupture. That is exactly why one disaster can suddenly multiply the number of alerts on your phone. The count rises sharply, but it may represent one evolving sequence rather than many independent crises. Seismologists become more interested when activity forms a meaningful local or regional pattern migration along a fault, unusual deformation, changing seismic mechanisms, or a sequence departing from established background behavior. They do not diagnose global escalation from a list of unrelated earthquakes in 5 countries. Each event is first analyzed within its own tectonic setting and its own sequence. This distinction matters because dramatic maps are excellent at showing where earthquakes happened, but they are poor at proving why those earthquakes happened. The same rule applies to tsunami risk. Not every large earthquake generates a tsunami. The fault must displace the seafloor in the right way, and depth mechanism, location, and bathymetry all matter. Indonesia's Flores earthquake generated tsunami warnings and measured small waves. Colombia's August 10 earthquake was deep and inland enough that the primary disaster was shaking and structural damage, not a major tsunami. This is why emergency agencies issue event-specific warnings instead of treating magnitude alone as a universal danger score. Context changes everything. There is also a media effect. A destructive earthquake makes people pay attention to every earthquake that follows, including events that would normally receive little international coverage. Notification systems compress the planet into one screen. A tremor in California, a swarm in Indonesia, and an offshore event in Japan can appear seconds apart, even though their fault systems are unrelated. Our perception has become global and instantaneous. The tectonic plates, however, are still moving at roughly the slow geological rates that have operated for millions of years. No credible scientist can use this week's international cluster to predict a specific next earthquake. Exact short-term prediction of the time, place, and magnitude of a major earthquake remains beyond current science. What scientists can do is map faults, estimate long-term probabilities, detect earthquakes rapidly, model aftershock probabilities, monitor deformation, and issue tsunami or shaking alerts when conditions allow. Preparedness is therefore based on known hazard, not viral predictions. If you live in an earthquake-prone region, the correct response is practical readiness rather than fear of a global countdown. Know the basic response: drop, cover, and hold on during strong shaking. Stay away from windows, do not run into stairways while the ground is moving, and expect aftershocks after a significant event. In coastal areas, if shaking is strong or long, follow local tsunami guidance immediately. Do not wait for social media to decide whether evacuation is necessary, and when a dramatic earthquake claim appears online, check the National Geological Agency, USGS JMA, BMKG, or another official monitoring center before sharing it. Fast information is useful only when it is accurate. So, what is happening? The Earth is active, as it has always been. In August 2026, several important earthquakes happened close together in time, and some caused terrible human losses. But the evidence does not show a single global earthquake chain linking Colombia, Indonesia, Japan, Spain, and the United States. Most of the pattern is explained by known plate boundaries, local sequences, and normal statistical clustering. The lesson is not to ignore the danger. It is to understand it correctly. Earthquakes are real, local hazards on a globally active planet. Watch the data, respect official warnings, prepare for your region, and do not mistake coincidence for a countdown.